Or is that better? Which do you prefer?
The
First one?
Yeah.
Okay. Alright. Let's have a look at the first homework then. The kinetic and potential energy. What was the first question then? Do you have it?
Where is the picture, please?
Who has the first question, please? Question 1?
Oh, okay, wait.
You have it?
No, that's the power engine. You see, I do it on Moodle, so it takes a long time to go back.
Do you have it?
Picture.
Yeah, go ahead, Andy. Oh, sorry. You said Adnan, do you have it?
No. Which number?
1.
From the beginning?
Yeah.
Estimate the maximum kinetic energy that you could have when you're running.
Okay.
When running. Where did the energy come from? Estimate your mass and top speed.
Okay, so I think I can be 100 kilograms, and then, I don't know, I can't run that fast.
Multiplied by 9,000.
I'd say maybe I could do
I've written
5. Yeah, but this is for me. Right. So, for me, I got 1250 joules. You will have a different answer. Where did this energy come from?
Food.
From my food. Okay, what's the next one then?
A physics teacher drops his coffee cup out of the window of 5-10 meters from the ground. How fast is the cup going at the moment of impact? Okay, so there's the cup and it falls. At the top it has potential energy. At the bottom it has kinetic energy, and they must be equal. mgh equals a half mv squared. M's cancel. So the v squared equals 2gh. So the v is root 2gh, which is root 2, 9.81 and 10, which is a thing.
14.
Sorry, what did you say? 14?
Yeah.
Okay.
Roller coaster is at rest at height of 100 meters above the ground. What is the fastest the roller coaster could have traveled at? When would it be traveling distance?
Okay, so this is actually the same as the last question. It has potential here, it has kinetic here. The fastest will be, of course, at the bottom. And we have mgh equals a half mv squared. So again, you get the same formula, v equals root 2gh, but this time it's 100, so what's it going to be?
44.29.
44 point. Again, so that's not too bad. What's the fourth one about?
A 1,200 kilogram car traveling at 120 kilometers per hour is brought to rest by the driver. A. Before the car is brought to rest, how much kinetic energy did it have?
Okay, let's do that part first. So I need to convert my...
33.33.
Oh yeah, it's that one, isn't it? 33.3 meters per second. So the kinetic energy is a half mv squared, which is 0.5 times 1200 times 33.33 squared. So you get a pretty big number. It got like 666.
533.
Yeah, 000 if I do 3. 666. Yeah, so, or 666. Well, if I suppose actually, sorry, that should really be a 7 if I'm rounding off.
Yeah.
No big deal though. 667 kilojoules. Yeah. That's part A.
B. Where did the kinetic energy go?
From the petrol.
Where did the kinetic energy
Oh, where did it go? Where did it go?
Brakes, heat, sound.
Heat. It's mostly heat at the brake pad. Heat in the brake pad.
A 50-gram lead weight is hanging to a pendulum.
Okay, so is this the last one?
No.
No. So you have 50 grams, you said?
50 grams.
So that's 0.050 kilograms, yeah?
Adding onto a pendulum of length 1 meter. The pendulum is pulled back so that it makes an angle of 10 with the vertical. What is the maximum speed of the lead?
Okay, so this will swing down and will be here. So this is what we have. So firstly, before I start, is that what you drew?
No,
No. What did you draw then?
I didn't even know.
Okay, alright.
I did not have to do it, so I left.
Okay, did anybody get it?
Answer.
The picture
No,
even?
No, I haven't, I've done like in the steps.
Okay. Are you happy with the picture?
Yes.
Yeah. So what happens is you pull this up, you let go, and it swings down. Yeah. So here, the potential energy here will equal the kinetic energy here, and this is like the ground. So we need to know this height, don't we? Yeah. Now if I make a triangle here,
No, not height.
Maximum.
What with the vertical? What is the maximum speed? of
Yeah.
the lead?
yeah, but before I can get to that, I need to know this height. Because I can say the potential here equals the kinetic here. So this side is 1 meter. How big is this side?
1 meter.
No, this part. Here to here. Anybody?
We use
Using your cos and your sine?
yeah.
Oh,
Come on.
So it will be like
No, I just, yeah.
cos 45, cos 10,
Cos 10.
0.9.
1 cos 10. Yeah. And this side here would be 1
Sine
sine
sine 10. So how big is 1 cos 10?
0.98, which is
0.98. So then if that's 0.98, how big must this piece be? If the total is 1, then this must be 0.02.
Okay.
You said 98, didn't you? 0.98, yeah. So, what?
How did you get 1 cos 10?
How did I get 1 cos 10?
From the calculator.
Yeah.
No. What?
What do we use it for?
Why use 1?
The length is 1. This is coming from the lesson. What lesson does this come from?
no.
No.
It's
Direction.
from,
This is resolving vectors.
But how did we know that the ground is just at the moment?
Yeah, like you're asking me why isn't the ground like here? Yeah. In fact, if you did put the ground down here, like let's say 1 meter away, you'll still get the same answer. So it actually is not important for this.
No, but it doesn't say in the question that there is the ground. So
No,
why can we
no, no.
assume?
You have to assume the ground is somewhere, true? You can't assume there's no ground, right? There's going to be a ground somewhere. Agree or disagree?
Yeah, I agree.
Agree. And I'm saying, if I put the ground here at the lowest point, or even if I put it 1 meter underneath it, I'll get the same answer in the end.
So can we choose like, oh, I'm gonna put the ground 1 meter?
Yes, for these problems, you can choose where to put the ground. Just like for the turning point problems, you could choose where to put the turning point. You'll get the same answer in the end. Okay.
Okay, after you know the cosine, 1 cosine 10 and 1 sine 10, how
Yeah.
did you know this side is 0.2? 0.02.
Here to here is 1 meter. Here to here is 0.98. So that means here to here must be 0.02.
And why is 1 meter?
Because it says in the question. I say this in the question. This is given in the question, isn't it?
Yeah, the
Yeah.
length is 1 meter.
The length is 1 meter.
But this is this length, not this length.
Yeah, but this
Yeah, well, it's something.
swings down.
Oh, yes, okay, that makes sense.
It goes, swings down. It's still going to be 1 meter when it swings down.
Yeah.
Still a meter, isn't it? It's not changing its length.
It's changed.
No. Look at this. This is 1 meter.
Yes.
Is it still 1 meter?
No.
Yeah.
Yeah. It's not changing its length, it's still 1 meter.
But in the draw, it's down.
1 meter swings down to here. Well, that's kind of bad. Swings down to what would it be like here. This is still 1 meter. What do you mean no? What do you mean no? This is 1 meter from here to here, and if it swings down, it's still 1 meter.
It swings down. It swings down, so it
No, we're
becomes.
talking about
No,
the
just like this, just like this, just like this, just like this.
It's
Not, it's not
It's a
going
rope.
down.
We're not talking
It's a
about
rope
the
with the
distance
ball, and
between
it's
it
going here and there.
between it and the floor. We're talking about the length of the
Swing.
rope. The length of the rope doesn't change.
It's attached here to the
I
thing.
think
Here to here.
we haven't done the pendulum one experiment.
Yeah, but still,
It's not two of it.
it doesn't matter where it is, it's still 1 meter.
Yeah.
Doesn't care.
It doesn't care where it is. Even if it's over here, it's still 1 meter.
He meant the distance between the ball and the ground. No.
Oh yeah, well that's fine. So like, this is 1 meter, and then what I did was I drew a triangle here, and we said, what was this piece here? Was no, not all the way, just 0.98. So if the total is 1 meter, then how much must this piece be? 0.02. Yeah.
Just all between it and
Yeah, from here to here, that little bit. I don't know if I can continue. Can I continue?
Yeah.
Are you sure?
Yeah.
Yeah. Okay. Potential energy. M. Do we know the M?
It's no.
Huh?
50 drops.
Yeah, we do know the M. Yeah. In fact, you don't even need, but you don't need to know the M because when I put the M in,
Cancel it.
it cancels anyways.
Yeah.
A half mv squared. So cancel.
Cancel.
Bring that up here to make it 2,
Yeah.
and then square rooted.
Okay, why you cancel the square?
I put a square root on the other side.
No, I mean why you cancel the square of the v?
I just said, listen, you're not listening to me. I put a square root on the other side.
Okay.
This lets me cancel it. Okay? No, that's okay, but you need to listen to me carefully. Right, what did we get here? What did you get for V? No, what I got.
0.62.
Yeah, that's what I got. 0.626
Yeah.
meters per second.
Oh, I didn't.
Yeah.
You know, it's 9.8.
He missed the 9.8 one. Okay.
Is Galway far from Dublin?
Tell me how this is related to this question, and I'll answer. I'll tell you it's more than 1 meter. That's the only way it's related to this question. It's not in Dublin. So,
3 hours, I think.
alright, is there one left here?
One.
Okay. What's the last one then?
Water was pumped up at 10 meters building.
This one. Okay, so hang on, let me just draw this. So you've got a tank of water here and a tank of water here. Yeah, and you said water is pumped up.
Water was pumped up a 10 meter building from one tank at constant rate of 2 kilograms per second into another tank.
Okay, so what happens here is every second
2 kilograms.
2 kilograms gets pumped up. So it's 2 kilograms per second. So every second 2 kilograms leaves. and 2 kilograms enters per second.
Yeah.
Okay? Right, so what's the first question then?
What are the energies at ground level and roof level of the roof?
What's the energy at ground level here of the water?
Kinetic.
Yes, maybe, but if it's in the tank, it's not really moving, is it?
Yes.
So it's at the ground, it's about 0. And what energy does it have up here? It definitely has potential. And again, I know it's moving when it comes out, but it very, very quickly just
But
comes
there
to
is
rest.
there is no energy.
Which part?
Like when it's moving from one tank to another.
What do you mean no energy?
Like
Kinetic energy.
when it's
There's
moving
kinetic
from-
energy as it's moving, yeah. But when it lands into the tank,
Yes,
then
there's
it's-
no energy.
no moving energy, no kinetic energy. But it still has potential because it's above the ground.
Yeah.
Yeah. Now, if you compare, this is at the ground, and then on the top there's potential energy. So this is at the top. So there seems to be a bit of a mismatch here because at the beginning we have 0, but at the end we have non-zero. So where did it get this energy from?
Does it really have
From
zero?
the-
I mean, the water itself.
From the ground.
At the ground?
Yeah.
Well, think about it. Like, let's say instead of water, it's coffee. Okay. So the coffee is just sitting in the cup. So does it have kinetic?
Yeah, because
It
it's
doesn't
not
have
kinetic
kinetic, but it has another form.
potential because of that.
But it's on the ground.
Then it's not potential, then it's maybe heat because it's coffee. I mean, it's probably something, some other energy.
Yeah, but in this context, we're only talking about kinetic and potential. Of course, everything has heat energy and other things too. Oh, what I think, are you saying that the potential energy came from the heat energy of the
Yeah.
cup? That actually is something we'll look at later, but that's not the case here. But good idea. It is something relevant, but not what I was thinking here. How did the water get from the ground to the top?
By
Pump.
By-
Pump. So the pump did work.
Yeah.
Yeah.
So the energy came from the pump.
So it's kinetic.
No. Well, yeah, okay, yeah. The pump gave it kinetic energy to
Yeah.
carry it to the top, but I don't really care about the middle part of the journey. I'm just looking at the start and at the end. So at the start it has no energy, and at the end it has potential energy,
But
and it came from the pump. It's almost like the pump gave it energy. So in other words, the pumping process did some work. Yeah, it's a bit like, here, like look at this, here is no kinetic or potential, but then when I lift it up to drink it, it's no kinetic, but it has potential, and this came from me, my arm. So my arm did work.
that's the kinetic
True.
energy.
In the middle here, it's moving. But at the start, when I look in here, it's not moving, and at the end, when I look in here, it's not moving. Now I know, okay, when it's coming out, it's moving, but it very quickly just stops then. If there was a hole here, and the water was leaking out, then it's definitely moving through. But because I said in the question it's a tank, I wanted you to imagine that the water just goes into the tank and then stops. Like a cup. You fill it up. What was the first question? What was the types of energy, was it?
What are the energies at ground level and roof level of roof?
Okay, so we better calculate it. So what I'll do is I'll look at a 2 kilogram bit of water. So what's the potential energy of that bit of water when it's up the top? It's MGH.
Yeah, it's 196.2.
And it's, you have it there, thank you. What do you say it was?
196.2 joules.
196.2 joules. So this little bit of water got its energy from the pump. What's part B?
How fast is the water being pumped?
Great, okay. The speed, is it?
Yeah.
Yeah. So now we can look at what you were saying, Sharif, about that it's and you too maybe, that it's moving in the middle. So my question is, how far is it moving?
You get the V.
You get the V, yeah. So if you look here, when the water just leaves the tank, here it has no energy, And here the pump gives it energy. It needs to give it enough energy to get to the top here, doesn't it?
Yeah, so it equals.
It equals this.
Yeah.
So you can just say a half v squared equals 196.2. Cancel, cancel, cancel. So what's the v? What's it about? 12, 14?
Yeah. I got it the slower way, but it's the same.
Oh, you got 14 as well?
Yeah.
Do you use UVATS or something?
No. I didn't equalize it to 196. I just did it the regular way.
MGH?
Yeah.
Yeah, okay, yeah, that's same thing.
Yeah.
Right, what's part C?
The water got its kinetic energy from the pump.
Good, yeah.
Therefore, per second, how much work is the pump doing?
Okay, so the work, I hope you can see this.
196.2.
196.2 joules per second is being done.
Mhm.
Because when I calculated this, I was looking at 2 kilograms, and I said in the question, it's 2 kilograms per second. So this is what the pump is doing every second. Every second the pump gives 196.2 joules of energy to 2 kilograms of water.
Sorry,
Every second the pump gives...
No, how did you know it's 1,000?
That's from the previous part here in part A. So this comes from part A. This one here.
The potential energy equals the work?
Yep, the potential energy equals the work. So the potential energy equals the work.
Why?
Because the water starts at the ground and moves up. It has no energy here and it has potential energy here. Where did this come from? It came from the pump. The pump gave it potential energy. Therefore, the work the pump did is equal to the potential energy it gave. This potential energy came from the pump. The pump gave it to it because it had nothing to begin with.
Okay. Can you zoom out?
Zoom out, yes. Is that the end of it or is there part D?
That's it.
That's okay. So we'll do the next one now in a moment. Power and efficiency.
It's a new lesson.
No, the next homework, and then we'll start a new lesson. How did these go for long? Did you get all of these? Yes? For homework? Okay. How many could you get at home? That's good.
I don't know, question 5, question
Same.
6.
I think they're the same as well. Did you get 5? Did anybody get this?
5? 6, yes, I got it.
You got all of this?
Yeah.
Nice, okay, but 5? No good, okay, yeah. But now you know how to do 5. 5 and 6 I've seen in exams. They're like exam questions. But now that you've seen it, if you see it again, it should be much easier.
So it will be in the exam.
Probably.
Could be. It could
Well,
be.
it must.
It must. It must.
Huh?
It must be.
Why must it be?
Because we took it.
No, that's not how I work. Yeah. Maybe that's how your teacher worked back home, but that's not how I
Is it
work.
necessary to show the diagram, show the figure in the exam?
Oh no, it's not necessary unless they ask for it, but it's strongly recommended that you draw to help understand the question.
The less you see.
If you can't draw it, you can't do it.
Exactly, yeah. Yeah.
And that's the problem.
That's the problem, but that's okay, we're working on it. Right, how many questions were in the power and efficiency?
6.
They're all pretty short though, aren't they?
The 6 one,
Still same.
Okay, let's look at the next homework then.
3 kilo.
What?